So this is a video, the first in a series on math foundations. It's part of the BC High School curriculum. It's also necessary to understand any higher math courses, um, and it's not that difficult. So today we're going to start by talking about sets, unions, and intersections. So a set is simply a collection of objects. So here you can see I have several collections of objects. The first collection I have is the color green, the color red, and the color yellow. So the way that we indicate that this is a set, one way you can do it is by putting these curly braces that mathematicians like to put around collections of objects. And we can just list the object out one at a time. So again, this is the set containing green, red, and yellow. So we can also have sets of numbers, as you can imagine, because this is math, but we can also have sets of anything, as you can see from the colors. So below here, below the set of colors, I have the set of the numbers 1, 2, 3, 4, 5, 6. I start with a curly brace, and then I write it like a list, one object at a time. First one, then a comma, then the second object, 2, and then a comma, and then the third object, 3 in this case, and then a comma, and so on and so forth. Okay? So notice that these sets are actually, they have a special property already, and that is that they are finite. What I mean by that is that you can actually count the sets in the objects here, and you will be able to stop eventually. Here there's only 3 objects, 1, 2, 3. Here there are 6 objects, 1, 2, 3, 4, 5, 6. So if you're thinking about what finite means, if we were going to try and define it more precisely later, we could define finite as any set that has a map between it and the first n numbers. So here there would be a map between this set and the first 6 numbers, the map that takes 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6, and so on. But we'll get to that in a later video. So we can also have infinite sets. This third set here is an infinite set, and I'll tell you why in a second, although you can probably see it already. So, and this also has another special property. The reason I've written it like this instead of a list with commas is because this set is infinite. That is, the set just keeps going on forever, right? This is the set of all objects n. And this bar here, this means such that. Just going to mark that down there for you. This means such that. So this is the set of all n, such that, or so that, n is an integer. So if you're in this set, that means you're an integer. And if you're an integer, that means you're in this set. So the way we write this, when we want to avoid writing a list, we can write a curly brace and then a symbol to indicate that these are objects with this vertical bar. And then we write the property that all our objects in this set has to have. So in particular, to be in this set, you must be an integer. So of course, probably one of the first things you learned in elementary school is that there are infinitely many integers, right? That is, you can't count them all because there's too many of them. There's too many of them. You'd have to count forever. Okay, so we can also do this. I didn't want to give you the false idea that we can't do what we just did here with the bar and the such that and the defining property with finite sets, because we definitely can. So here is a place where you might want to use the bar notation in a finite context, and that's because this is the set of all B, such that B is a bacteria inside of you. Now, I'm not a microbiologist, but I know that there's like many orders of magnitude of bacteria in you. Billions, trillions, probably someone's going to correct me and tell me it's even more than that. There's a lot of bacteria in you. And so this is the set that contains all bacteria with the property that it's a bacteria inside of you. Okay, so that's sets. Sets are just collections of objects. So moving on. We have these sort of set operations. We want to do things with sets, okay? And so it's always best to start things with an example. And so the example I have is this. I have 2 sets here. I have a set E and a set O. The set E is the set of all objects with the property that they are even integers. So E is the set of even integers. Similarly, O is the set of all objects where the object is an odd integer. So O is the set of all odd integers. So it might be useful to be able to combine sets. So if you're thinking about this, it's like I have two bags here. I have a bag E and a bag O, and inside of bag E, I have all the even integers, and I have a bag O, and inside of bag O, I have all the odd integers. So what I can do is I can empty out my bag E and I can empty out my bag O into a new bag that we call E union O. This right here is the union symbol. And aptly, it is a U. So E union O is the set of all n such that n is an integer. Why? Because every integer is even or odd, and we emptied our bag of even integers and we emptied our bag of odd integers into this common bag, E union O. Okay, so here's a finite example, S and T. So I have S, and S is equal to, it's a bag or a collection, and in the collection in the bag, I have 1, 2, and 3. Similarly, I have a different collection, T, and in T, I have 2, 3, and 4. Okay, and so I can take S union T. So what do? I empty everything that's in S and I empty everything that's in T into S union T. But now this situation is slightly different. In my E union O example, there was no repeats. There was no even integer that was also in the odd bag, and there was no odd integer that was also in the even bag. But in S, I have 2 and 3, both in S and T. So in S, there's 2 and 3, and in T, there's 2 and 3, right? So when I throw them into the bag, suddenly I have 2 2s and 2 3s. But in sets, when we do a set operation like union, when we have a repeat, we just throw it away. Sets don't care about repeats. As if you had a magic bag, if you threw 2 of the same object into the bag would destroy one of the objects. It's sort of like some sort of like quantum bag principle. You can't have 2 objects of the same kind in the bag at the same time. Not identical objects anyway. So we have S union T. It's going to be 1, 2, 3, 4 in a bag. Okay? And so more formally now, after giving you a couple of examples, if A and B are sets, then A union B is equal to the set of all things where the thing is either in A, or it's in B, or it's in both. Here we use or in the inclusive sense, and that it can be in A, it can be in B, or it can be both in A and B. The only condition to be in A union B is that you're in at least one of them, but possibly you're in both of them. Okay? So moving on, the last thing I would like to talk about in this video is the intersection of sets. So intersections are sort of like, if unions are like ors, intersections are like ands. So let's do an example first. So I have 2 bags here. I have, or sets if you like. I have a set S, and it's equal to 1, 2, 3, 4 in a bag. And I have a set T, and it's equal to 3, 4, and 5 in a bag. So S intersect T is the set. So we want to take things that are in both sets when we take the intersection. So I look at S and I look at T. I'm going through the elements one at a time here. I see that I have 1 in S. Is 1 in T? No, it's not. So it doesn't wind up in S and T. Similarly, I have 2 in S, but I don't have 2 in T. So I throw it away. It doesn't wind up in S intersect T. Okay? This symbol here, I probably should have said, is the intersect symbol. Sorry, that's not a very good arrow. It's not this bad arrow that I've just drawn. This is supposed to be an arrow pointing to this sort of upside down U. Okay? So carrying on, I have 3 and 4, and I see that 3 and 4 also appear in T. So 3 and 4 are in S, and 3 and 4 are in T. So they are both in S intersect T because they're in both sets. So finally, I have 5 in T, but I don't have 5 in S, so I don't put it in the intersection. Okay, so that's S intersect T. Now it could happen that if I take the intersection of two sets, that there's nothing that's in both sets. So for example, in Q intersect R, you'll see I've put nothing in between the braces, and that's because Q has blue and red, and R has purple and orange. Now, blue is not in R, and red is not in R, and purple is not in Q, and orange is not in Q. So there's no thing or element that's in both Q and R. So that means that there's nothing that goes into Q intersect R, and we have a special symbol for that. This is what we call the empty set. You can think about it like being like an empty bag before you go grocery shopping. You haven't put anything in there yet. It's just, there's nothing in there. It's just a bag. But it's not nothing. It's an object, right? And the object is the empty bag, and we call this the empty set. Okay? So similarly, if we remember our set E and O from the previous page, E was the set of even integers and O was the set of odd integers. So if we take the collection of things that are both even and both odd, well, there's nothing that's both even and odd in the integers. You're either even or you're odd. So when I take their intersection, I get nothing, right? So E union O was all the integers, because every integer is either even or odd. And E intersect O is the empty set, because there is no integer that is both even and odd. So finally, I'm just going to write it. I've written out a little formal definition here, which will hopefully make a bit more sense after some of those examples. So A and B are sets here. So if I have A, this upside down U means intersection. A intersect B is equal to the set of all things X, where X is in both A and B. So the only way you wind up in A intersect B is if you're in A and you're in B at the same time. You can't just be in one or the other, or neither. So that's it for this video. In later videos, I'm going to more formally talk about set memberships, set differences, and a few other things. And hopefully start building up towards functions. And anyway, I don't want to get too far on what's coming, but you'll see when you look at my website and look at the videos.